The first multi-axial failure criteria I'd like to discuss is Tresca's yield condition, and this is a condition that's useful for polycrystalline metals. And the criteria is rather simple. It simply says that the maximum shear stress has to be less than or equal to the shear stress in yield. And what's important to recognize in Tresca's criteria is that we are talking about the overall maximum shear stress, so over any possible direction of the system. In other words, on any plane in the system, if you look at the shear stress on that plane, we have to keep the maximum value over all planes less than or equal to tau y. So this is the basic idea of Tresca's yield criteria. There's a nice visualization of this is if we make a Moore diagram and we plot normal stress in some arbitrary direction x prime and shear stress on that same plane, then what Tresca's yield criteria says is that the three circles of stress, when you draw the Moore circle in 3 dimensions, have to lie between two parallel lines, one whose value is minus tau y and one whose value is tau y. So if you're inside these two lines here, then we're in the elastic range. So in other words, if you draw the Moore circles and they are between the two horizontal lines here, then we'll have an elastic state of stress. And as soon as the circles touch that line, then we're going to have yield in the system. So this is the idea of Tresca's yield criteria. So basically, to evaluate it, you have to draw the Moore circle for the system. One of the advantages of this of the Tresca yield criteria is that it's relatively easy for hand computations, especially if you have two-dimensional states of stress. It's easy to draw the Moore circle. If you have a 3D state of stress, you have to figure out the third principal stress, either because it's easily identifiable or you can do an eigenvalue calculation to determine it, but then you can always draw the three circles, then you can check the criteria here. So it's easy to do in that case. The other nice thing about Tresca's yield criteria is that it has a relatively good connection to the actual physics associated with yield in metals. Yield in metals is associated with movement of defects or dislocations, and the dislocations or defects, they move on what are known as glide planes, and they move due to shear stress on the glide plane. So suppose I have some kind of defect on a glide plane whose normal is n, and it's moving in the m direction, then the shear stress that's driving that dislocation is simply sigma transpose n dotted with m will give me the shear stress in that direction. And what Tresca's yield criteria is doing is saying that we're going to look at the resolved shear stress over all possible planes, so all values of n and all possible directions of glide m. So that's the idea of, or the connection between the resolved shear stress notion. Now, in a real metal, there are only fixed planes and fixed directions in which you can have glide, but in a polycrystalline metal, there's a whole randomization of these glide planes and in directions. So it has a nice connection to this idea of resolved shear stress, which is sometimes known as Schmidt resolved shear stress. The other thing that's important about the Tresca yield criteria is that it's compatible with another experimental observation, and that observation is that yield in metals, polycrystalline metals in particular, at say normal temperatures, ordinary things like room temperature and things like that, is independent of the pressure that is applied to the system. And so let's just take a moment here to define what we mean by pressure. Pressure is defined as the mean normal stress in a system, and if we in a tensorial setting, we think of it as, say, sigma vol, which is this pressure P times the identity, so that's the matrix with 1, 1, 1 on the diagonal. And what the observation says is that yield in polycrystalline metals is independent of sigma vol. Okay, so let's think about what remains if we subtract sigma vol off the actual stress. We'll get a new stress quantity I'll call S. This is known as the deviatoric stress in the system. And what observation shows is that yield in polycrystalline metals really only depends on the deviatoric stress. So it's independent of sigma vol. So when we're going to check the stress, we should subtract it off. And let's think about what that means in the case of the Tresca criteria. Suppose I had a state of stress shown here in purple, so three-dimensional state of stress. If I add a volumetric stress or hydrostatic stress by changing the pressure, say by p hat on the system, the only thing that's going to happen to the three circles of stress is that they're going to translate horizontally along the normal stress axis. The radii are not going to change if I add some type of value of pressure to the system. So in particular, if you think about the stress in the principal coordinate system, it has a diagonal form, and so if I add onto it any pressure, state of stress or hydrostatic state of stress, all I'm going to do is change the intercepts here. So I'll get sigma 1 plus p, sigma 2 plus p, and sigma 3 plus p. Oops. So this is the state of stress that we're going to get if I add a hydrostatic state of stress to some given state of stress. And all that's going to do with respect to the Moore diagram, if I go ahead and plot the Moore circle for this state of stress, is it's going to translate it horizontally to the right by an amount p. Okay, so this is the idea of pressure independence, is that the yield of a system should not depend on the hydrostatic pressure on it. So you can add or subtract hydrostatic pressure to any given state of stress, and it shouldn't affect yield. And the Tresca criteria here is completely compatible with that notion, because if I add hydrostatic pressure to any state of stress, it's just simply going to translate the Moore circles horizontally here. It will not grow their radii in any way, shape, or form, and thus there's no additional propensity of the material to reach the yield limits, which are these horizontal lines at tau y and minus tau y.